What if I told you that Earth's future ice ages are written in the stars, or more precisely, in our planet's cosmic dance around the sun? And what if the most groundbreaking research is telling us that humans might have accidentally canceled the next glacial period entirely? Our planet's climate has never been static. For millions of years, Earth has cycled between long glacial periods, what we call ice ages, and shorter, warmer interglacial periods like the one we're experiencing right now. These massive climate shifts weren't random. They follow cosmic rhythms that scientists have only recently begun to fully understand. These rhythms are called Milankovitch cycles, named after Serbian mathematician and geophysicist Milutin Milankovitch, who in the early 20th century meticulously calculated how variations in Earth's orbit affect the distribution of solar energy across our planet's surface. What makes these calculations particularly remarkable is that Milankovitch performed them all by hand, decades before computers could verify his work. His theory initially faced skepticism, but has since become the cornerstone of paleoclimatology, the study of ancient climates. The brilliance of Milankovich's work lies in identifying three distinct orbital variations that work in concert to influence Earth's climate over tens of thousands of years. The first is eccentricity, the changing shape of Earth's orbit around the Sun, which shifts from nearly circular to slightly more elliptical over a cycle of about 100,000 years. When the orbit is more elliptical, seasonal contrasts become more pronounced, with potentially dramatic effects on climate. The second variation is axial tilt, or obliquity, the angle at which Earth's axis leans relative to its orbital plane. This angle isn't fixed. It wobbles between 22.1 and 24.5 degrees over a 41,000-year cycle. Today, we're at about 23.4 degrees. When the tilt is greater, seasonal differences intensify. Summers become warmer and winters colder. This has profound effects on how ice sheets form and melt, especially at higher latitudes where the seasonal differences in sunlight are most dramatic. The third component is precession, the slow wobble over Earth's axis, similar to a spinning top that's about to fall over. This wobble completes a full cycle roughly every 23,000 years and determines which hemisphere faces the sun during different parts of the orbit. When a hemisphere experiences summer while Earth is closest to the sun, perihelion, that summer will be more intense and the opposing winter more severe. These three cycles, operating at different frequencies, overlap and interact to create complex patterns in how solar energy reaches different parts of Earth. Sometimes they amplify each other. Sometimes they partially cancel each other out. The resulting patterns are what Milankovitch proposed as the pacemaker of ice ages. For decades after Milankovich's death in 1958, his theory remained controversial. The breakthrough came in the 1970s when climate scientists analyzed deep-sea sediment cores, cylindrical samples drilled from the ocean floor that preserve millions of years of climate history. These cores revealed temperature patterns that matched Milankovich's orbital calculations with striking precision. The oxygen isotope ratios in fossilized microorganisms preserved in these sediments provided a temperature record that clearly showed glacial cycles aligning with orbital variations. This connection isn't just academic, it's visible in Earth's landscape. The rhythmic layers in sedimentary rocks, called cyclostratigraphy, often reflect these orbital cycles. Glacial moraines, Great Lakes basins, and even the stone patterns in some ancient buildings all bear witness to ice sheets that once covered vast portions of North America, Europe, and Asia, all driven by these cosmic cycles. But recent research has taken our understanding to extraordinary new heights. An international research team, including scientists from UC Santa Barbara, has analyzed an unprecedented million-year climate record. By examining marine sediments, ice cores, and other paleoclimate indicators, they've created the most detailed reconstruction of past climate cycles ever assembled. Their work confirms that glacial cycles follow a predictable pattern dictated by orbital variations, but with fascinating new insights about how these cycles interact. One of the most intriguing findings concerns a climate mystery known as the 100,000-year problem. For the past million years, ice ages have followed a roughly 100,000-year cycle matching Earth's eccentricity pattern. But before that, glacial cycles followed a 41,000-year pattern, matching the axial tilt cycle. Why did this shift occur? The new research suggests it wasn't a simple switch from one orbital influence to another, but rather a complex phase-locking phenomena where multiple cycles began to synchronize in a new way. The research also provides unprecedented clarity on the timing of ice ages. By matching changes in ice sheet size and deep ocean temperatures with variations in Earth's orbit, scientists can now predict with greater confidence when the next ice age would naturally begin. And here's the remarkable conclusion. In the absence of human influence, the next ice age would be expected to begin in approximately 10,000 years. This timeline emerges from analyzing how the current orbital configuration will evolve. Right now, Earth's orbit is relatively circular, and the northern hemisphere summer occurs when Earth is farther from the Sun. This arrangement reduces summer heat in the north, where most continental landmass is located. As orbital precession continues, eventually northern summers will become hot enough to prevent snow and ice from persisting year-round at high latitudes, the critical condition that prevents ice sheets from forming. The precision of these new predictions is extraordinary, the result of combining advanced climate models with unprecedented paleoclimate data. These models can now account for complex feedback systems involving ice albedo, reflectivity, ocean circulating patterns, and atmospheric composition that either amplify or dampen the initial orbital forcing. The scientific understanding of Milankovitch cycles has undergone nothing short of a revolution in recent years. While the foundations laid by Milankovitch have stood the test of time, contemporary researchers have built sophisticated new frameworks that address long-standing puzzles in paleoclimatology. Perhaps most significant among these advancements is the development of the Generalized Milankovitch Theory, or GMT, published in 2024. Unlike the classical theory that treated orbital variations as simple climate-forcing mechanisms, GMT recognizes the Earth's climate as a complex, non-linear system where orbital factors interact with feedback loops in sometimes surprising ways. The theory emerged from the collaboration of climate physicists, mathematicians, and Earth scientists who realized that treating Milankovitch cycles as isolated drivers missed crucial dynamics. At the heart of GMT lies an elegant mathematical framework that explains one of paleoclimatology's most persistent mysteries: the mid-Pleistocene transition. About 1 million years ago, Earth's glacial cycles underwent a dramatic shift. Before this transition, ice ages followed a dominant 41,000-year cycle, matching Earth's axial tilt variations. After the transition, they mysteriously shifted to a 100,000-year cycle, matching orbital eccentricity. For decades, scientists were perplexed by this change. Early theories suggested it might represent a fundamental alteration in how Earth's climate system responds to orbital forcing. Some proposed that gradual cooling over millions of years caused thicker ice sheets that required more time to build and collapse. Others suggested change in atmospheric CO2 dynamics were responsible. But GMT offers a more nuanced explanation: phase locking. Rather than a simple switch from one dominant cycle to another, GMT demonstrates mathematically how the climate system began synchronizing multiple orbital cycles through non-linear interactions. Think of it like musical instruments that start playing in harmony rather than independently. The 100,000-year cycle emerged not because eccentricity suddenly became more important, but because the climate system began responding to combinations of orbital variations in a new way. What's revolutionary about this finding is that it reveals how Earth's climate can undergo dramatic shifts in behavior without requiring any change in the external forcing mechanisms. Instead, it's the internal dynamics of the system that evolve, creating new patterns from the same inputs. Supporting this theoretical breakthrough are remarkable advances in how we detect and analyze Milankovitch cycles in Earth's geological record. One of the most exciting developments comes from a team of researchers who pioneered the use of convex optimization algorithms to enhance the detection of orbital signatures in stratigraphic records. This mathematical technique involves a long-standing challenge in paleoclimatology: distinguishing true orbital signals from background noise in rock layers and sediment cores. The method works something like noise-canceling headphones for geological data, filtering out random variations to reveal the subtle patterns of orbital influence. When applied to existing climate records, these algorithms have identified Milankovitch patterns with unprecedented clarity, confirming some predictions while challenging others. Perhaps even more fascinating is the geothermal evidence unveiled through studies of ferromanganese crusts in the Atlantic Ocean. These crustal formations grow extremely slowly over millions of years, accumulating trace elements and isotopes that record shifting ocean chemistry. Recent analysis of lead isotope variations in these crusts have revealed unmistakable patterns matching orbital cycles, providing an entirely independent confirmation of Milankovitch theory. What makes this evidence particularly valuable is that it's governed by different processes than the oxygen isotope records traditionally used to study paleoclimate. The matching patterns in these independent records dramatically strengthen our confidence that orbital variations truly drive glacial cycles. Have you ever wondered how scientists can be so confident about climate patterns from millions of years ago when weather forecasts struggle with accuracy beyond a week? What techniques would you use to study ancient climate if you were a paleoclimatologist? Share your thoughts in the comments below. These research breakthroughs have refined Ice Age predictions in ways Milankovitch himself could have never imagined. Where earlier models could only make rough estimates about the timing of glacial cycles, modern climate models incorporating GMT can provide much more precise forecasts. They account for the complex interplay between different orbital parameters and the various feedback mechanisms that amplify or diminish their effects. One of the most crucial insights from this research concerns the phenomena of phase locking between different Milankovitch cycles. Imagine three pendulums of different lengths swinging independently. Usually they follow their own patterns, but occasionally they synchronize in ways that create periodic moments when they all align, producing a much stronger combined effect. Similarly, Earth's orbital variations occasionally align in configurations that strongly favor either warming or cooling. The new research has identified these critical alignment patterns with far greater precision than ever before. It's not just a matter of individual cycles reaching their peaks, but specific combinations of orbital parameters crossing critical thresholds together. For example, when moderate eccentricity coincides with minimal axial tilt and precession that puts Northern Hemisphere summers at aphelion, the point when Earth is farthest from the Sun, conditions become optimal for ice sheet formation. Conversely, when high eccentricity combines with maximum tilt in northern summers at perihelion, closest approach to the Sun, ice sheets face triple jeopardy from warming influences. The research has revealed that these alignments follow specific mathematical patterns that can be projected into the future. By analyzing how these patterns have triggered climate transitions in the past, scientists can identify critical thresholds with much greater confidence. This explains why some seemingly similar orbital configurations led to full glaciations while others produced only minor cooling episodes. Another groundbreaking aspect of recent research concerns how different regions of Earth respond to orbital forcing. Traditional Milankovitch theory focused heavily on conditions at 65° north latitude, where most continental landmass capable of supporting large ice sheets is located. But new studies have shown that tropical and southern hemisphere responses play critical and previously underappreciated roles in global climate transitions. For instance, recent findings demonstrate how orbital variations affect monsoon systems, which in turn influence ocean circulation and carbon cycling, factors that can amplify or dampen ice age triggers. Modeling these interconnected systems have revealed that ice ages often begin with subtle changes in tropical precipitation patterns, years before any significant cooling appears in northern latitudes. The more comprehensive understanding of regional responses has dramatically improved our ability to interpret the geological record. Features previously seen as anomalies or contradictions now make sense with the expanded theoretical framework. Sites where climate proxies seem to be out of sync with Milankovitch predictions are now understood to be responding to different aspects of the orbital forcing or showing expected regional variations. The integration of these regional differences into global climate models represents one of the most significant advances in paleoclimatology. Rather than treating Earth as responding uniformly to orbital variations, modern models capture the complex mosaic of regional responses that eventually cascade into global climate shifts. This nuanced approach has resolved numerous paradoxes in the geological record and substantially increased the predictive power of Milankovitch theory. While Milankovitch cycles have reliably orchestrated Earth's climate for millions of years, something unprecedented has entered the equation: us. Human activity has introduced a wild card into this cosmic climate dance, and the latest research reveals just how dramatically we're altering these ancient patterns. The natural cooling trend that would eventually lead to the next ice age in approximately 10,000 years is now competing with anthropogenic warming at a scale that has stunned climate scientists. Since the Industrial Revolution began, carbon dioxide levels have skyrocketed from around 280 parts per million to over 420 parts per million today, a concentration not seen on Earth for at least 3 million years. This extraordinary increase has effectively short-circuited the orbital climate control system. Recent models suggest that the critical CO2 threshold for overriding natural cooling trends is around 350 parts per million, a level we surpassed decades ago. At current and projected concentrations, human-induced greenhouse warming is now powerful enough to counteract the cooling effect of any orbital configuration. This represents an astonishing development. For the first time in Earth's 4.5 billion year history, a single species has gained the power to override astronomical climate forcings. The implications are profound. Multiple climate simulations now indicate that the next ice age could be postponed by at least 50,000 years, and potentially much longer if fossil fuel use continues at current rates. Some models suggest we may have effectively canceled the next several glacial cycles entirely, potentially creating an artificially extended interglacial period lasting 100,000 years or more. This raises fascinating questions about the competing celestial and terrestrial influences on our planet's climate. For millions of years, astronomical forces operated as the master control system, with Earth's internal climate feedbacks amplifying or dampening these orbital signals. Now, human activity has essentially seized the climate controls from the cosmos, at least temporarily. The scientific community is engaged in a vigorous debate about whether humans could or should deliberately manage these cycles in the future. Some researchers suggest that once we've stabilized current warming trends, future generations might actually want to carefully maintain greenhouse gas levels to prevent ice ages, which historically caused massive ecological disruptions and human migrations. Others argue that such geoengineering would be misguided, that we should allow Earth's natural cycles to resume once we've addressed the immediate climate crisis. They point out that our understanding of climate systems, while vastly improved, remains incomplete. Attempting to permanently alter Earth's relationship with Milankovitch cycles could have unforeseen consequences that might prove catastrophic. This controversy highlights our evolving relationship with planetary systems. Throughout human history, we've been at the mercy of climate changes driven by forces we neither understood nor controlled. Now we find ourselves in the paradoxical position of having accidentally gained influence over processes that operate on geological timescales. The scientific toolbox for studying these interactions continues to expand in remarkable ways. Advanced Earth system models can now simulate the complex interplay between orbital forcing, greenhouse gases, ocean circulation, ice dynamics, and vegetation changes with unprecedented detail. These models incorporate machine learning algorithms that identify patterns in paleoclimate data too subtle for human researchers to detect. One particularly promising direction involves using quantum computing to model the non-linear interactions between different components of the Earth system. Classical computers struggle with the computational complexity of fully coupled climate models that span astronomical timescales. Quantum approaches may soon allow simulations that capture the full richness of these interactions across thousands of millennia. New proxy records are also revolutionizing our understanding of past climate responses to orbital forcing. Beyond traditional ice cores and ocean sediments, researchers now analyze cave formations, ancient pollen, tree rings, and even compounds preserved in fossil leaves to reconstruct past climate conditions. Each new proxy adds another piece to the puzzle, helping scientists refine their understanding of how Earth responds to orbital variations under different boundary conditions. These research directions are not merely academic exercises. They provide crucial context for understanding anthropogenic climate change. By clarifying how Earth's climate naturally responds to different forcings, scientists can better isolate and quantify the human impact on the system. This improves both hindcasting, explaining past climate changes, and forecasting, predicting future ones. The ethical dimensions of these discoveries are equally compelling. Should we be concerned about delaying ice ages? After all, glacial periods have historically been challenging times for human civilization, reducing habitable land, disrupting agriculture, and forcing mass migrations. Preventing such disruptions might seem beneficial. However, natural cycles have shaped Earth's ecosystems for millions of years. Countless species have evolved adaptations to these cyclical changes. By disrupting these patterns, we may be removing evolutionary pressures that maintain biodiversity and ecosystem resilience. The long-term consequences of such disruptions are difficult to predict but potentially severe. There's also the question of timescales and intergenerational ethics. Decisions we make today about greenhouse gas emissions will affect Earth's climate not just for centuries, but potentially for tens of thousands of years. This forces us to consider our obligations to future generations in ways that human societies have rarely had to contemplate. Additionally, while preventing an ice age might benefit human civilization in some ways, it doesn't address the immediate threats posed by rapid warming. The pace of current climate change, occurring over decades rather than millennia, gives natural and human systems little time to adapt. The potential prevention of a far future ice age offers little consolation for coastal communities facing rising seas or regions experiencing intensifying droughts and heat waves today. The story of Milankovitch cycles and human interference illustrates a profound transition in our species' relationship with Earth. We have moved from being passive subjects of astronomical climate forcing to active participants in determining Earth's climate future. This power brings enormous responsibility to understand the systems we're affecting, to mitigate harmful impacts, and to make decisions that consider the welfare of future generations and the entire biosphere. As we continue to refine our understanding of these cosmic climate controls and our growing influence over them, we face choices that no previous generation of humans has had to make. The research into Milankovitch cycles isn't just revealing our planet's past. It's helping us navigate an unprecedented future where humans have become geological agents in our own right, capable of redirecting climate patterns that have persisted for millions of years. If you enjoyed learning about how we humans might have accidentally canceled the next ice age, hit that like button and subscribe to see more videos exploring the mind-bending interactions of cosmic forces and human activity. What other astronomical phenomena would you like us to explore in future videos? Let us know in the comments below. And as always, stay insanely curious.